let's have a look at asymptotes. Right. So we know curves always bend towards our asymptotes when we're drawing our pictures. And the key thing is vertical asymptotes, curves never will cut it. And this brings up one of the biggest misconceptions about asymptotes. A curve can cut other types of asymptotes. A curve can cut a horizontal asymptote. A curve can cut an oblique asymptote. It just cannot cut a vertical asymptote. Right? Now, the reason being is because horizontal and oblique asymptotes are really mean nothing when you're around the origin. It's describing the behaviour out at the extremities of the curve. So it can cut it when it's near the origin. Now, when you're comparing to infinity, near the origin might be 10,000. But that's still going to be closer to the origin than it is out of infinity. There's a little menu I use. Most of the graphs, or a lot of the graphs, I shouldn't say most, a lot of the graphs we deal with are simply polynomials, and they might be as fractions. So if I've got a function which is a polynomial on a polynomial, I could do a polynomial division and write it as the quotient plus the remainder on the divisor. That tells me a lot of information. I know the bottom of the fraction can't equal 0, so that's going to find me my vertical asymptotes if I simply look at the bottom of the fraction. Now, QX, the quotient, is the horizontal or oblique asymptote. Theoretically, it might even be a curved asymptote. No reason why it couldn't be a parabola. It still ends up being an oblique asymptote because remember, it's what happens at an infinity. So the curving bit around the origin is irrelevant. I just know it's going off to that branch of the parabola. So QX will always be the other asymptote. Now, the top of the fraction then will tell me if it cuts that other asymptote. If I can solve it, if I can make that fraction equaling 0, then y equals the asymptote. And so I must cut it. Let's look at this. X plus 3, x minus 2, and x minus 1, x plus 1. So we know, well, let's do the polynomial division so x squared minus, x squared goes into x squared once. What do you know? We get a remainder of x minus 5. It's alright, I could break it up that way. 1 plus x minus 5 on this one. So I know we have x-intercepts. X-intercepts is where the original function equals 0. They're nice and easy to find. So minus 3 and 2. Y-intercept, that's another easy one to find, so 6. Vertical asymptotes, bottom of the fraction can't equal 0. So plus or minus 1, let's draw those in. Notice I've dotted them. Dotted them because they're not part of the graph, it's just a boundary. Horizontal asymptote will be 1. Question is, will this cut the asymptote? Yes, indeed it does. At x equals 5. Top of the fraction would be 5. So I know it's going to go through that point there. That should be enough to draw the curve. Curve's got to bend towards the asymptote. So I know on the left hand side it must do that sort of hyperbolic shape. Because it's got to go through the x-intercept of -3 and it's got to bend towards the asymptotes. I know it does not cut the vertical one, but I also know it does not cut the horizontal one over this way. So there's only one thing it can do. Now in the middle, it's got to go through 6. Okay, I've got 3 options. I could have like a U shape, or an upside down U shape, or I could have an inflecting shape. But it does not cut the horizontal asymptote. So now there's only one thing it can do, and that's the U shape. Then we go to the right hand side, far more interesting. It's got to go through 2, it's got to go through 5, 1, it's got to bend towards both of these asymptotes. So it's not going to be like the hyperbola here. What's it going to do? Well, I ran out of room, so it made it a bit hard to show what I was trying to do. But what it's going to do is it'll come through 2, it'll come through 5, it'll keep going up. But remember, it's got to bend towards the asymptote. So at some point, it's got to turn and come back down, and then inflect and go towards the asymptote. Not a great picture there because I ran out of room, but that's the only thing it can do. We know it doesn't keep going up because it's got to bend towards the asymptote, so it must come back down and bend. So there's our graph. Lovely, isn't it? Correct answer is yes. Yes, it is lovely. Alright, let's try this one. So I've got a cubic on the top. Let's do a division. So our quadratic into the cubic, and well, x substitute in, get a remainder, and we can keep going. So minus 1, and our remainder, and that's as far as we can go. Okay, there's my fraction. Okay. X-intercepts. So I've got 2, 1, and negative 1. Y-intercept, substitute in, we get negative 1/3. Vertical asymptotes are at negative 2 and 3, and an oblique asymptote at x minus 1. It will cut the oblique asymptote at x equals 1. Mind you, we knew that already because we know there's an x-intercept, so it actually confirms that. Is that enough to draw our graph? And I say yes, it is. Let's start from the left-hand side. I've got no points on the left-hand side, yet I know what the graph's going to do. Because I've got to bend towards those asymptotes, but I do not have an x-intercept. So there's only two things I could do. I could be stuck in the little triangle down the bottom, or I could have like a hyperbolic shape. But there's no x-intercepts, I've got to be in the little triangle. Now, here's the interest. So in the middle, I had to go through all those points and I had to bend towards the asymptotes. But remember, that oblique asymptote means nothing in between negative 2 and 3. It's telling me what happens out at infinity, out of the extremities. So don't let the oblique asymptote distract you. All it's really doing is going through those points that I've identified and bending towards the asymptotes. And again, how high up does it go? How far down does it go? Well, I'd need to do some calculus to locate those points exactly. So later on, once we've done some calculus, we'll be able to do a better graph. But as a rough sketch of what the shape is, we've got it there. And so as I say, on the right hand side, we'd be stuck in that little triangle. And look at that, we got a beautiful little graph, and all I had to do was a polynomial division, and it just gives me so much information by just looking at the equation itself. And so I've left this to, I guess, the last bit of our curve sketching, but hopefully you can appreciate that this idea of looking at an equation and trying to pick out the features is a really good way of drawing graphs rather than simply plotting points and hoping for the best. You're actually fixing on specific things, trying to find the key information to draw a reasonable sketch for whatever you have to do. Okay, we shall add those particular ones. A very old phone network now, of course, but my phone's still on us. Hey, it works. What can I say?